So we are talking about Newton's law of cooling. Welcome back once again. This is now a continuation from, we're still on the topic of heat transfer. Now this time around, we want to talk about the rate of cooling as analyzed by Newton. So in Newton's law of cooling, how long a body takes to cool is affected by the environmental temperature or the relative, the difference in temperature between the environment and the body which is undergoing that cooling. That's the focus of Newton's law of cooling, and we shall see as we go. So in other words, the temperature of the environment also affects the rate at which the cooling will take place. Here's our illustration. If you have this body, which is at temperature TW, and its surface area is A, and then the fluid substance, meaning the environment, is at temperature T, then the rate at which heat is going to be lost, the cooling rate, will be like this. It will be alpha A, temperature of the body, minus temperature of the environment. This alpha is the coefficient of conductivity or heat transfer coefficient. Then A is simply the surface area in square meters. So if you have to put it in to state Newton's law of cooling, this is where we're saying that the surface temperature of an object changes at a rate proportional to its relative temperature, meaning that the rate at which heat is going to be lost will be proportional to that temperature gradient between them. Now, let's consider that we're looking at heat being lost per unit area from, heat moving from one point to the surface, through the surface onto the other side of the surface. It could be that this is a wall. We'll soon look at a diagram to illustrate this. So here, this is in a fluid. The rate of cooling will be for unit area, meaning we're saying where area is 1 square meter. Alpha for point A. Please, this is not area A. This is alpha and a small a there, meaning the heat transfer coefficient at point A for the fluid multiplied by the temperature difference, meaning TA minus T1 where it is going. Now here I want TA minus T1 to be on one side alone. We're trying to come up with an expression. So what I have is alpha dot, Q dot over, meaning I divide through by this alpha A. So I have TA minus T1 on the other side. This is what we're talking about. I'm talking about heat moving from point A to point 1. The temperature at point A is higher than the temperature at point 1. So here I'm applying Newton's law of cooling. But how is heat going to move through this thickness? I have to apply Fourier's law of conduction, where we need to have the lambda, as well as we've been given the thickness and the two temperatures, so T1 minus T2. So for this, we're done. Let's now look at how heat will move from here to here. When we're done, we'll also consider how heat is going to move from point 2, going all the way to point B. Meaning this is now the outside environment. So for point 1 to 2, this is where I said we're applying Fourier's law of conduction. So I have lambda divided by the thickness, then multiplied by the temperature difference, which is T1 minus T2. So once again, I don't want these. I want this to be out of here. I just want T1 minus T2 to be here. But all the same, I will emphasize that at some point, we may use this expression as it is. For now, as I'm trying to come up with the overall expression, I want T1 minus T2 to be on one side of the equal sign. So I make it a subject. I have Q dot, then there's X over lambda equals T1 minus T2. Then I also have the last part, which is where now the heat is supposed to come out of the surface and into the environment. So it is going to move from point 2 to point B. So the rate of heat transfer per unit area is alpha for point B multiplied by this temperature difference, which is T2 minus TB. And making T2 minus TB the subject, I have Q dot divided by alpha B. So this is my equation 3. Now what are we going to do? We're going to add the left side of the equal sign, add all of them together, and equate to what is on the right hand side. Let me remove this. People could be failing to see those numbers. Okay. And I have to bring back the pointer. Okay. All right. So here, adding all the left hand side of the equal sign for equation 1, equation 2, and equation 3, this is what I will have. For equation 1, I had Q dot divided by alpha A. Equation 2, I have this Qx over lambda. Equation 3, here we have it. U dot over alpha B. Then equation 1, I have TA minus T1. Equation 2, there's T1 minus T2. Equation 3, I have T2 minus TB. The beauty about this expression is that these are positive, so they're not going to change things there. So if I get rid of the brackets, I will have no trouble coming through. I'll have no drama. Because here, I was basically using the brackets to make sure that we can identify where they are coming from, and it's easier to trace them. With that in mind, I've thrown away the brackets. On this other side, I can notice that this Q dot is common for all the three. So there I have it outside the brackets. Then inside the brackets, this is what I have. So this is equal to, then I can have my TA minus T1 plus T. Basically, I've just removed the brackets. But here is the secret. Here's, I mean, not even the secret, but here is what we can see from here. This is T1, negative T1 plus T1. It's as good as saying T1 minus T1. So this is out. This is 0. Then I have positive T2 minus T2. It's as good as saying T2 minus T2. Again, it gives us a 0. This cancels out. After this, what I should have now is this. Here, I don't want all this. I want to make this the subject. So, first of all, here, everything has disappeared. I only have TA minus TB. And I don't want this thing here. I want this boss to remain alone because I'm looking for the rate of heat transfer per unit area. So what I have now is Q dot is equal to TA minus TB over everything that I have here. So that is the expression that I have. TA minus TB over 1 over lambda A, 1 over alpha A plus X over lambda plus 1 over alpha B. Remember, this is a standard model. Suppose the wall had several layers, this must be extended also to incorporate those layers, because this is for a single layer wall undergoing some cooling. Let's see, what if we were to just talk about the overall coefficient? Here we just pick what was the denominator, what was making up the denominator, 1 over alpha A plus 1 over lambda plus 1 over alpha B. Meaning that if I have to make U the subject, then it will be 1 over alpha A plus X over lambda plus 1 over alpha B. That gives us the U, the overall heat transfer coefficient. Now, if I had to put this representing Newton's law of cooling, then I'll have this with a U for unit area. But if I've also been given the area, then this Q becomes capital letter Q, and I can have U and A, and the rest is just like that. So here we're saying U is the overall heat transfer coefficient. Let's pick up an example. In this example, we have a tank which is made of steel. Thickness of the tank, 10 millimeters. The water inside the tank is boiling at 90 degrees Celsius. Outside the tank, the temperature is 15 degrees Celsius. Then thermal conductivity for mild steel, it is 50 watts per meter Kelvin. Then for inside where the water is boiling, inside the tank is 2,800. Outside the tank, it's 11 watts per square meter Kelvin. So what do we need? Let's calculate the rate of heat loss per unit area and also the temperature of the outside or on the outside of the tank. Here is our information given. We have the thickness of the tank, 0.01, because it was 10 millimeters. Then temperature inside, 90 degrees Celsius. Temperature B, TB, meaning on the outside of the wall, on the outside of the tank, the environment, 15 degrees Celsius. Then again, the heat transfer coefficient for the fluid inside the tank is 2,800. For the fluid outside, the environment there, the air outside, the heat transfer coefficient is 11 watts per square meter Kelvin. For the steel, the mild steel, what I have is 50 watts per meter Kelvin as our thermal conductivity coefficient. This is per unit area, meaning area is 1. So we can now see how this is going to work out. The solution, we are going to invite back this expression where we have TA minus TB, everything divided by 1 over alpha A plus X over lambda plus 1 over alpha B. So TA is 90, then the temperature outside is 15. Alpha A inside the tank is 2,800 is the coefficient. X is 0.01. Lambda is 50. On the outside, the value of alpha, which we are calling alpha B, is 11. So with this substitution, we have 819.975 watts per square meter. What about the rate of heat transfer, or the temperature on the outside of this tank? So again, we agree that the heat transfer rate remains constant. So we can apply now the equation that works on the outer end, where we are applying Newton's law of cooling. So alpha B, T2 minus TB. Substitution. This rate of heat transfer is 819.975. Then I have my 11 for the outer end. T2, we don't know, minus 15, because the temperature on the outer wall, on the outside of the tank, is higher than the temperature on the environment, on the surroundings. So that's why I have it as T2 minus 15. Here you make T2 the subject, play around with your algebra, feel free to maneuver. The answer that you should be able to have is this, 89.5. Almost 90. It's like the thickness of this is quite low, so the temperature inside, on the outside, very close to what is inside there. away. That is what we have there. 9.54 degrees Celsius. Let's pick up another example. So here I have an electric hot plate at 400 degrees Celsius. That's where things have been maintained. The plate is this, and this plate is heating a solution boiling at 80 degrees Celsius. Then it's contained in an iron vessel, wall thickness 50 millimeters. Then there's enamel 2 millimeters. And the heat transfer coefficient for the boiling solution, it's 10 kilowatts per square meter Kelvin. Then the thermal conductivities for the cast iron and enamel are 8 and 2.5 watts per meter Kelvin. Let's pick up the information. Temperature at A, which I can even call temperature 1, is actually 400 degrees Celsius. The temperature on the outside, or rather, going now, this time things are flipped. We're going inside the boiling solution. It's 80 degrees Celsius. So with that in mind, I proceed now to say I have the X1, which is 0.05 meters. It was 50 millimeters as the thickness. X2, which is the enamel, is 2 millimeters. So 2 divided by 1,000, you get 0.002 meters. Alpha B, talking about the coefficient, heat transfer coefficient for the outer, or the rather inside the boiling pot, it's 10 kilo. I decided to shade it yellow here so that we don't miss it. Kilo represents 1,000. So 10 times 1,000 gives us 10,000 watts per square meter Kelvin. Lambda 1 is 80 there, because this is the coefficient of thermal conductivity for cast iron. For lambda number 2, which is enamel, because here it said respectively, meaning first material is this, second material, which is enamel, is this value. So I have 2.5 watts per meter Kelvin. So there I have it. Lambda 2.5 watts per meter Kelvin. Let's get to the working. So what I have here, I just need to find the rate of heat transfer. I have lifted the formula the way it is, but I have edited in between to accommodate the two layers, because this is now a multi-layer wall. So then what I have now is 1 over alpha plus x1 over 1 over lambda 1, x2 over lambda 2 plus 1 over alpha b. Now, one thing you will notice, there is no mention of alpha A. This plate is hot and it's heating up the kettle. It's heating up that pot. So let me just go back there. So this electric hot plate is helping us to keep a solution boiling. Now the vessel that we're using, basically behaving like a kettle, is there. It is keeping this solution boiling at 80 degrees Celsius. Now with that in mind, here we are saying this, where we are supposed to have alpha A, it's a hot plate, it's a solid, there's no solution there. What we have is X1. So to avoid breaking down the formula the way you had it, I'll just get rid of the first part and leave everything else the way they are. So I have thickness 1 and going all the way to the other end. So the starting temperature and the final temperature remain like that. Then here, all these, they have what they're representing. So the inside temperature is 80. The temperature of the hot plate is 400. So that's TA minus TB. Then I also have X1, the thickness of the material, starting one, the cast iron is 0.05. The lambda for cast iron is 80. The enamel is having a thickness of 0.002, 2 millimeters. 2 millimeters converted, this is the one, 0.002. Lambda number 2 is 2.5 watts per meter Kelvin. Then alpha B was 10,000 watts per square meter Kelvin. Take your time, enter all this in your calculator. The answer that you should have is this: 209,836.066 watts per square meter. Because this is asking us to find the rate of heat transfer per unit area. The heat rate, the rate at which heat is being lost for each unit area or for each unit surface area. So this is what we have now. Once again, this time around, I'm just having 3 questions for you to try out. I've already planted the answers so that you can see how things are moving. Okay, thank you. We'll link up in the next one. Like I said, for you to easily pick up when I post a recording, subscribe and don't miss out the next one.